Hey Thomas,
Hey, Luca.
how are you doing? I know there's been a lot of work um, this week.
Yeah, that's but finally you see me in a happy state, like things work instead of they should be working.
Yeah, yeah. So what are we talking about is, since R1 came out, we had our own R1 deployed through Lightning, and that's great. Now we want to kind of layer new optimizations using Thunder and all the optimizations that are coming out of DeepSeek itself and others that we have in mind. And of course, Thunder is our primary source of optimizations. And running the 671 billion model with Thunder at the level we wanted to has been a bit of work, but it's kind of a trial by fire. Like if a compiler can run the whole massive thing and just go with it, I think we're at a stage where that goes pretty far. So
Yeah,
kudos to you and the team for
yeah.
achieving that.
So one of the interesting things is that uh, I mean you always have the problem that the model like fits almost on an H-time H100 machine.
Yeah.
And I guess everyone has seen this, right? The rich people just say, yeah, go, let's just take H200. The
Yeah.
NVIDIA people say, well, let's just take GB200. And
Yeah.
of course, like normal people, they are in a bit of a pickle. But so actually, we thought that it was interesting that the L40S, which we've been using for the demos in the Thunder sessions too, they have not 40 but 48 gigabytes of memory, and so actually you can fit the entire model and a bit of KV cache onto like 16 of them. So you
Yep.
can run it on two 8 L40S nodes. And so
Yeah.
that
Yeah.
has been interesting. The other thing that I think is interesting here is that it connects to what we did the last two things. Like we talked about how the interpreter runs and acquires the program, and then how the JIT component and now we have this little thing that kind of overloads the terminology a bit, but not too bad. It used to be much worse when the interpreter was called JIT too.
Yeah.
But so the JIT component that translates from torch calls to thunder calls, and we looked at that last time. And today we're going to look at the next thing, like how these two things and the transforms that we had before in this last summer and fall, and how these connect into one big thing that you know as the thunder.jit function, right?
Yep.
And
Yep.
so incidentally, and this is where like the loop closes, incidentally, in order to enable running R1, one of the things we need to do is like split up the computation into several parts. And of course, you could do that in advance and then only compile the bits that belong to one GPU or one machine. But it's invariably more fun to do this, like take the entire model, compile it, and then split it up. And
Yep.
in order to do this, you need some more fine-grained control over these things, right?
Yeah, and it's very nice because at this point you can trace the model on your CPU because it's just computation. You can split it up on your CPU, then you can distribute the fragments, um, and uh, and this gives you a lot of flexibility. Even for example, if you think about serializing those things and just doing it once, you know, so things are gonna look very very interesting, specifically for these very large models. So what we're seeing is that this week has been interesting for me because um, I had a little bit of personal stuff today. So I had a meetup in London on Wednesday night. It was the PyTorch London PyTorch meetup, and I talked I gave a short talk there. It was at the Lightning office location. And I showed some studio, of course. There was a lot of excitement there, some startup people that want to use it, and it's great. And then I talked about my struggle that day, loading a 70 billion model for fine-tuning using FSDP1. And it's not working. It's impossible to do with lazy loading. So if you use lazy loading and FSDP1, you can't possibly load the weights in there unless you do like very serious magic that it's beyond what's documented and what you should do. And then I had to try, because I didn't want to show like Thunder necessarily. I just wanted to show PyTorch, and I used FSTP2. And FSTP2 forces you to kind of wrap your model in very specific ways in this callable that you run on top of your model. But then if you have just a single checkpoint, just not sharded, just a single checkpoint, the 70 billion, you download it, and you want to load that, that's not possible out of the box. You need to kind of lazy load parameter by parameter, and then call a function to shard it. But doing that is not that it's documented anywhere. It's in TorchTune. You need to go into TorchTune, and we'll put it in the GPT because it's a good thing to have there too. But ultimately, dealing with these large models, you could see that the whole system, and I'm not blaming PyTorch at all. Everything is built on PyTorch nowadays, but the system has grown from a place where this was not a problem to the place where right now. And, being able to take a computation and just reason about it, manipulate it without allocating a single byte on the GPU is actually pretty great. And JUX people have done this, although the manipulation of that is not that simple. In JUX land, I think we have something a bit easier to manipulate in Thunder. But so next week we'll talk about probably FSTP and how we do that with FSTP. Yeah. But today we need to kind of take the connection between what we explained at the JIT and the JIT last week, and what will allow you to kind of reason about these things. So today we're going to talk, and let me share my screen, about, this is not the right screen. This is the right screen. All right, we will talk about the journey of the computation, right? And if you followed our previous episodes, then probably everything will start clicking. If you didn't, maybe this is a key of it, to navigate our previous episodes. We need to do a job of putting good titles or subtitles to our episodes, but this is a work in progress.
We should have a competition, find the best title.
Or we could use one of the R1s that we deploy to find. No, it's not multimodal. A good multimodal model to a Qwen VLM to find the right title, or maybe on the transcripts. Actually, much easier. All right. So everything starts with an NN module, right? So we have our NN module. Old school.
The R1.
So I need to draw it like this, or no, actually like this.
Doesn't fit on one screen.
No, exactly, right? You need 16 iPads.
Remember, a few years ago, there was this visualization of these language models, and the BERT one was the small one, and the larger one was GPT-2 or BERT XL, and those were huge.
They're massive, right? Okay. Yeah. It's interesting.
So we have the model, but we want to use Thunder, right?
Right. Well, we want to make it faster or distributed, or it's so massive that we cannot even deal with it. And how do we deal with it? We need to acquire it, as we said a million times. And then what do? We run the JIT, which in turn runs the interpreter, of course. So here is there's the interpreter.
No. It
Sorry.
not.
What happened?
If you call JIT,
Oh, sorry.
then the
Yeah.
first thing that happens is
Yeah.
that uh, uh,
This is the
there
JIT
will
function.
be there will
Yeah.
be functions transforming the module.
Yeah.
Like the
You're right.
module gets
Forgot about
wrapped in the Thunder module, and
it. Yeah.
then there are all the transforms get to take a shot. Like there is a method. Each transform can provide a method transform module, and then for example, the materialization puts them on GPU and initialize it, or the quantization like quantizes things. And so
Yeah.
these will be the transforms of modules. And then it doesn't
So sorry.
actually call, yeah,
Yeah. Just one thing is that the transform module will basically, this standard module will have the original module, like
right.
we have a reference to it, and it kind of exposes things that are important to Thunder. So it's the module, the equivalent of the NN module in for Thunder, because then we talked about transforms, and transforms have multiple hooks. One of the hooks is the transform module, right?
Yeah.
And and all these hooks start at different points of the life cycle. So what we're doing here is we're traversing the life cycle. Here you call JIT. JIT will wrap the module into Thunder module. Then we'll go into the transforms that have been provided to the JIT call, right? They're
Yeah.
like maybe transforms here, and they say, okay, this transform, iterate through them. Oh, has overwrites a transform module function method, and that will take the Thunder module and do some transformation to it. One of them, for example, is providing a function to load and save the state dict and so on. And all these things need to happen at the level of the module itself, not the computation, right? Because
Right.
these deal with the module. Okay, great. Awesome.
Yeah.
All right.
So you mentioned the FSTP and the sharding. Like there's also a transform for state dicts, and there's actually a forward backward. Like you can go both directions with that. So for FSTP, you would have a thing that shards the state dict, and actually one that unshards the state dict. And because we want to make it a bit memory efficient, we do this like submodule by submodule.
Yep.
And yeah, so
And this is exactly, by the way, what my struggle with FSTP2 was. Like, how do I unshard just in time so that I don't run out of memory? And you need to really know the APIs to do it. And the nice thing about this transform, FSTP transform that we have, is that it just does it for you because it's within the transform. It's something that happens as a part of that. Yeah. Nice.
yeah, and so after that, the JIT method is almost done. All it does, it gives you back the Thunder module, which is, among other things, it's a callable, right? And so in this callable, or in the thing that is hooked up, the callable that is hooked up inside the Thunder module, there is where the actual like processing happens once you call it, right?
Yeah.
And so if you call this callable, like once you run it, then we need to, and this is then where we also use the interpreter and the JIT that we talked about the last couple
Yeah.
of times. But when you call this, the first thing we need to check is whether we need to run the interpreter, right?
Yeah.
And for this, we need to see whether we already did it for the
Yeah.
configuration that we need. And so one thing we mentioned in great detail last time is that we condition this on the metadata of the inputs.
Yep.
And in addition to the to the input metadata, There also is state of the world that we need to take into account. So, for example, the torch, like global state modifiers, things like no grad or automatic multi-precision, or if we're talking about FSDP, like no sync, where you skip synchronization between nodes.
Yep.
And so these states of the world are captured in a data structure called the cache info. And so with those two things, the inputs and the state of the world, we can run, if we have cached prologues, we can run the cached prologue, and it will either like say, no, I'm not the right prologue, go find something else, or it will say, I'm the right prologue, here's the computation function and what you can pass to the computation function. But
Yep.
so obviously the more detailed case is when we have a cache miss.
Yep.
And so let's look at that.
So this is the, of course, just to summarize that, we have some inputs or some input metadata. Oh my God. Okay. And well, let me rewrite it. Sorry. It's horrible. Okay. We have some input metadata. And we have some cache info. And then we need to decide if this is a cache hit or a cache miss. So in case of hit, we just rerun, and we decided by running the prologue.
Right.
So the prologue is this trace, this function that is callable that will tell us, is it a hit or not a hit? If it's not a hit, with the mechanism that we talked about, where we hoist all the conditions on what we proxy, and so we kind of see if something in the computation has changed in a way that will change the path of the computation itself. And then if we hit, we just rerun the computation trace that we already created, the callable for the computation trace. If we don't, then here's what we do. Right? And what do we do is we run the JIT again, of course, because we potentially know nothing about that computation. So we need to acquire it again. Right.
Yeah. And so if we are in this case, we need to acquire the initial trace first.
Yep.
And this is, of course, done by running the interpreter as the helper of the JIT component that we showed last time. And so this will run through the program by the interpreter and translate all the torch into the thunder equivalents by the virtue of the JIT component and the thunder torch subsystem.
And we know exactly how this happens because we covered it in the last couple of episodes.
Right.
But that's only the end of the beginning.
Yeah, and then we have like our initial trace, and so we're in the Thunder world. But so there are a number of things that we still want to do before we're like letting it loose. And so one of the things that we do is that we functionalize the computation. And what this means here is that we eliminate the in-place operations, or rather resolve them into out-of-place operations and copy operations. And so this is something we need to do in order to be able to reason about things more easily. Yeah. So
in place means, just to clarify, in place means, I don't know, I have a tensor A and I have a tensor B and they're compatible, like either I broadcast or they have the same shape. And I do A dot add underscore B, and the values of B will be copied into the storage or added to whatever values are in the storage of A. And that is something that you can either keep like that or transform in a copy plus the addition, the autoplace addition, but then you need to replace all the references to that thing after the computation. So of course, we have all the computation and we need to do the right thing there, but potentially you can do it. The disadvantage is that you potentially duplicate the memory instead of keeping it what it was. But other than that, you should be able to produce a trace that is equivalent with no in place.
Yeah, so the compiler people, of course, want to have the keyword SSA here, like the
single
symbol statement assignment. But so the other part is that, of course, like it is questionable when the in place is even that useful, because essentially, if you don't need to hang on to the thing that you override with the in place, then it will go out of scope anyways in the next thing, right? So it's not memory saving of in place. To my mind, is always a bit dubious. And I even wrote a blog post about it, like back in the day, back in the Torch script days. But okay, so we run this functionalization, and then comes the first hook point for our things. Then comes this pre-prologue.
This is pre-prologue transform, right?
Yeah, transform traces pre-prologue, I think is the method name. It's a method on the transform class or on the object. And so this is where a lot of the transforms do quite a bit of work. So for example, the distributed, because you need to have a way to adjust the prologue and the computation. For example, for distribute, you need to update the shape checks, and for quantize, you need to change the operations to quantize operations, and you need to change the checks also to the quantized shapes.
Just to clarify, right? Because if we run distributed, it means that, for example, say you shard a weight, and so the weight is a part of the inputs for the computation trace, right? So it's not a part of the input for the module, so you don't see the weights, but if you shard, you'll have a weight that is smaller. And so the input to your computation will be something that is smaller along one dimension, the dimension through which you sharded. And so when the transform breaks up your model or shards in this case, the FSTP doesn't break up your model, but kind of reduces the size of your weights because it distributes them, then the prologue that will check, right, whether, things are the same or not, and it needs to unpack things and pass them to the computation trace, which is purely functional, needs to know that that thing is presumably smaller than what you traced it with. Because remember, we trace with metadata that are from the full model, because we're not really running the model, so we can afford running something fake, right? It's just the metadata that we run through. So the initial trace will have the weights non-sharded, right? But then when we get into the transform, we need a computation trace that will see the inputs among which the weights are that have sharded weights. And that's where this the transformation here will tell it, okay, transformation, things are changing, weights now are at a dimension in which they are smaller. Try to make it like self-contained. Yeah. The same thing for quantization, of course, because now the tensor will be different. You do the initial trace without quantization, then you transform to be quantized, and obviously some of the tensors will have a different procedure.
Yeah. And so you have these, and notably, it you have a chance to modify the prologue, and you have all sorts of things, because some of the other transformations, they consider the prologue fixed. And so the next thing that happens, and this is where the signature kind of needs to be fixed. The next thing that happens is that if needed, we apply autograph. And this, of course, involves like doing this forward backward thing, computing the backward for the forward, which we do through the Thunder auto differentiation system. And so after that, you can't really reasonably change signatures much anymore. And so if you want to have something that changes like the number of arguments or introduces additional things or makes things non-differentiable or whatever, you need to do it before the autograph hits, right?
Yeah, exactly. So just to clarify, and this is why it's so important, like not that everything is a pass. Oh, it's a compiler pass. It will just be at the pass. Every transformation you make needs to happen at a very specific time. Because after something happens, like autograph runs, you either trash everything and rerun autograph, or you won't have a chance to autograph what you added to the signature. It's very simple. So that's why the transforms need to have our a very specific life cycle moments and everything needs to happen in an orderly fashion.
And of course, we learned this iteratively, like in the very initial version of Thunder. There was only one sort of transform, and it only happened after autograph. And I think you couldn't even do transforms when you had autograph or something. But so, of course, we saw that it was limiting us, and so we changed it. So we now have this hook point there.
And also, maybe one last thing, reminder. Autograph will need, if you need to backward, you need to save more things for the backward. Meaning that what the forward computation produces will be an augmented version of what it would have produced if autograph wasn't there. And so that's also why you may get into kind of, more stuff being produced by the forward computation trace, right?
Right. You need to reach this peak memory, right? When we had
exactly. Otherwise, where's the fun of going out of memory?
Yeah. Otherwise, NVIDIA would have a hard time selling those beefy GPUs. But yeah, so after the autograph, there isn't another hook point. Maybe there should be, but so after that, we do the transform for execution. And this is where we, in several steps, go from the Thunder world back that uses proxies and stuff back to calling actual torch functions and things and other executors, where we replace, if you remember how we did transforms, or when we did custom operators, we had the meta function. And this is like when you call the pre-prolog and all these. And then there was the implementation. And transform for execution takes those symbols, and instead of using the meta functions, it replaces them with calls to the implementations, essentially. And of course, there are also the fusion passes where they combine things automatically through NVFuser or torch compile. And so these also happen here. And then after the transform for execution, we're not done yet. So there also is a post, and it's called post optimization transform. So we needed names that kind of tell you when it is, but we expected that we would be adding more intermediate steps. So there might be a 3B at some point if we need it. And in fact, like the rematerialization for checkpointing, that comes in between that's part of the do autograph, but it could be in between 3 and 4, right? Okay, so the post optimization transforms, this is also an important point where you already know all the things that are happening. And so, for example, the CUDA graphs goes there, or if you want debugging information, we had that too, that we like captured the memory allocated from the debugging transform. And so those go in the post optimization transform. Yeah, so after that, you really have the final trace, and you can make it callable, right? Of course, the trace can be printed as a Python program, and then you compile the Python program into a callable, and you have the callable, right?
Yeah, we have the prolog
Yeah, you have
function.
the prolog, you have the computation fn, and the epilogue fn, which is kind of the maybe least interesting one. And
well,
so
epilogue, like prolog, as we always said, goes from module world to functional computation world. This is a purely functional,
right.
the style that JAX people like. So straight line, assignments, and purely functional. Everything that happens in there comes from either the arguments or a byproduct of some computation. Nothing else happens. And then epilogue goes back, like wraps things up. Like, for example, in transformers, there's ample use of very complex data structures going into forward methods, right? So you have data classes or dictionaries, blah, blah, blah. And so the prolog will say, okay, let me unpack everything here. I'll create arguments for the computation. And then at some point, the computation will output more stuff. And then the epilogue needs to package it up, back up into the right data structures that are supposed to go in output of the computation. And this is where, what will happen in the epilogue.
Right. And of course, if you have these functions, you actually need to run the three of them. But yeah, that's the easy part after you have gotten all these things, right?
Right. And then, of course, you have the functions, and then the 6 is run the functions.
Yeah,
and
interestingly, I wonder if it's outside the list, run the functions.
Oh, yeah.
But yeah.
It could be here. Yeah. And interestingly, an optimization that would just throw it there and then forget is that sometimes, the prolog will not give you anything. You could just run the computation raw. It's a bit more risky, but even nothing is changing, it's a performance boost. Because you don't do any unpacking or anything, and it just, update your inputs in the values, but we know that the values are not really important because we don't have any data dependent control flow, so you can just run it. All right.
Yeah, or you have your bespoke adapted to your use case caching layer.
Exactly.
And so one thing we did quite a while ago, I think in the summer, is that we split out getting all these things and running the prolog. That was one unit that we split out because we wanted to be able to call the computation function ourselves without the prolog, and just do the prolog thing when we need it, and have more control about this. But so while we were working on the R1, we figured that it might be even interesting to have even more control. And so if we look at these steps, maybe can you zoom out a bit or go up? Yeah, like this. So one thing we noticed is that the interpreter is not like the fastest Python interpreter on earth. And one thing we did was that we hacked around it by by monkey patching the call to the interpreter and replacing that with something that just says, yeah, here's the traces, go take them if the input shapes match and the conditions that we seem.
You basically can you can serialize, at any of these points, you can say, okay, now if I could, maybe instead of doing that repeatedly or doing that with something changes, if you split things up and kind of get a handle from this point, right, and you just take that instead of starting from the beginning and so on. I think one of the beauty of this is that everything is here is in Python, so it's quite easy to then at this point kind of say, okay, what if I go in here and just get that, and then or even save it to a file, and then get it back or in memory and reuse whatever at whatever point. I think it gives you a lot of flexibility.
Yeah. So
Yep.
we found out early that we want to split out the 0th step here in this, and we hacked around it creatively, as as anyone would do. But we found that when we did the R1, we found that we wanted to have this pipeline parallel where you split up the computation into several parts. And so this would mean that you only want to run the 0th step once, and then do the other steps multiple times, because that will already save a ton of time, right? When we traced the Llama 1 billion model in autumn, we always had 1 minute or so to trace the model for the step 0. And if you can eliminate that, good. Or reduce the number of times you do that. Just we sometimes want to remove running the prologue. And as we progress, it seems that it would be cool to have even more detailed control over these things. And so one of the things we do now in order to enable a less hacky way to split out running the interpreter is to make that a proper separate function that you can call individually. And this is pretty neat, but it's also you need to take care of this cache info parts. And so that is also a bit tricky, that you need to kind of you need to know where you capture the state of the world exactly.
Yep.
And how to propagate that.
Yeah, I think one of the very fascinating things at this point, finally we have, we're getting Thunder to a place where you can really get creative, is that since you can run these things purely, and I'm pointing at here, right? Purely if you have a CPU, not even that powerful one, then you can say, okay, if this is the CPU, I'm going to do a lot of this 1, 0, 1, 2, blah, blah, blah. And then if I want to do, for example, pipeline parallelism, instead of taking the trace, I can break up the trace already, and then make sure that each one of the GPUs sees one of the traces, and so I don't have to reproduce the same process too many times, and I can use it. I can do it. I can view the model without allocating any memory, which is what you can do with meta device in PyTorch already. But here you get the full computation. So you can apply transformation, you can apply parallelism, have a full graph, full transform thing. And remember, we are doing things at this level and so on. And then if you need to optimize kernel, run with actual implementation and tensors and do kernel on the fly kernel optimizations, that's what you do, but you do it at a stage where your trace is small enough to fit a single device and directly on the device, on the fragment of the computation that pertains to that device, or to a fragment of the weights that pertains to that device, which is depending on what kind of parallelism you're doing.
Yeah, and of course you might also get ideas about more caching and also eliminating some of the later steps. Yep. So interestingly, if you look at these 5 steps, they are increasingly, of course, they're increasingly specific to the actual. They get less abstract, and it's really some sort of lowering. The do autograd already also needs to like figure out which things you need to do in order to hook up the autograd at the end when you run the computation function. And then the transform for execution, of course, this needs to like find the functions, and those functions will have kernels at the backing them, right, for the actual computation. And the CUDA graphs that also is like one of the lower level things, right?
Yeah.
So one upshot of this is that it gets increasingly hard to cache these things, because suddenly you don't need to cache a few Python objects, but you need to cache the GPU kernels.
Yeah.
And so, there's lots of exciting things that you can
Yeah,
do.
but I would, as a take-home message, and then we're done, it's really all about the control, you know?
Yeah.
Moving forward, if you read the DeepSeek V3 paper, or if you're looking at their stuff, it's all about control of the minutia of, the computation. But of course, you can do it raw, very raw, like they're doing, or you need to have a vehicle for those things. And we believe with Thunder, we are building that vehicle, and that will allow people to run all these things by going through these 5 points plus the 0th one, without messing with their original source code. Because if you think about it, messing with the original source code is dangerous. You don't want to mess with your model just to optimize it, right? Because you may be computing something entirely different. And so that's how the future, I think, looks like. So thanks for bearing with us. We've gone, I think at this point we've gone full circle. Next week we'll focus on what happens with FSTP, which is very interesting because as we were saying today, you're changing your prologue, you're changing the inputs to the computation. There's really nice effects on how you load the weights from an unsharded or sharded checkpoint, and how you save them back in a form where you don't even notice they were sharded before. And
obviously here at the Thunder sessions, we're all about the nerd out, but in the end, like things like this FSTP will show how it can be a quality of life thing.
Yeah, exactly. So we'll compare with other type of experiences. All right. Thanks a lot, Thomas. It's been great.
Yeah. Thanks, Luca. You have a great weekend.
Yeah. And get a good rest after the R1 adventure. Not strong, adventure. Bye, everyone.
See ya.